For example 4, we have a slightly different situation. We are given the second derivative of f and we have to find f. So if I have the second derivative, I wish I had the first derivative because I know how to do those problems. But since the second derivative is the derivative of the first derivative, then if I want to find f prime of x, I know I can do that by using antiderivatives. And since I'm going to have f prime and I want to find f, then I'm going to have to use antiderivatives again to find what f is. The big idea of this example is to use antiderivative twice. Now we have to find f, and not the most general one, but the only one that goes through the point 0, 4 and that goes through the point 1, 1. Since, and you know why you're given two pieces of information, probably because you're gonna have two Okay, so let's find f prime of x if we know the second derivative. Since all of them are just powers of x, I'm just gonna apply that power rule. 2 plus 1 will be 3, so I know I'm gonna have 12x cubed over 3 plus, since here the exponent is 1, I'm gonna add 1 to it, which is 2 over 2 minus 4. And now this is the tricky part. 4 is the same as 4x to the 0. So when I find the antiderivative of this will generate a 4x. And the only reason I know that is that when I take the derivative of negative 4x, the derivative is negative 4. So that's why a term with x shows up here. And it's because it's, you can think of it as x to the 0. So 0 plus 1 is 1 over 1. And remember that we have to add a constant. Now, if I knew some condition related to f prime, let's say that they gave me f prime of 0 is 5, I will have a way right now to find out how much c is. But that's not the case. The two pieces of information I know are about f. So in here, I cannot substitute the x to find out how much c is. I'm going to have to find it on the next step. Naturally, if I see this expression, I can cancel out the 12 with the 3, and that will give me 4x cubed, and the 6 with the 2, and that will give me 3, so that I have a simpler function to find the antiderivative of. Alright, so now I have that, and now let's do it one more time. I'm going to find the antiderivative of this expression. Since all of them are still powers of x, then I can just apply the rule. X to the third will become x to the fourth over 4, and the 4 that was initially here stays, plus, and then this is going to be 3x cubed over 3 minus 4. X will become x squared over 2, and then the plus c will become plus cx, and then I'm gonna add d. Now I don't want to put the cherry on top as a c because I know that the constant in here is not going to be the same as the constant that I have here, so I have to pick another name for a constant. So I'm just going to choose d. You could have chosen anything else, but you know, if we have c, then the next one will be d. This is just to indicate that the difference, if I'm taking the derivative of f to obtain f prime, you know that the derivative of this would be 0, so I can call it anything I want. Now in this function I don't know c and I don't know d, and that's why I'm given two pieces of information, because I have two unknowns and I'm able to set up two equations. But first let's just it's not f prime, it's f. Let's just simplify this expression. The 4's will cancel out, the 3's will cancel out, so I have x to the 4th plus x cubed minus 2x squared plus cx plus d. So I know that f of 0 will be 0 to the fourth plus 0 to the third minus 2 times 0 squared plus c times 0 plus d, and that is 4 because this is given information. So I know this is 0, this is 0, this is 0, this is 0, so d is 4. So I found one of the constants. Now let's find, with the other piece of information, let's find the other constant. F of 1 will be 1 to the fourth plus 1 to the third minus 2 times 1 squared plus c times 1 plus d, which is 4, equals 1. From the second piece of information, f of 1 is 1. So this is 1 plus 1 is 2, minus 2 is 0, so these cancel out. C times 1 is c, plus 4 equals 1, so c is negative 3. So since I found the two constants, then I can complete my answer by saying that f of x is x to the fourth plus x cubed minus 2x squared plus c is negative 3x, or I can write just minus 3x plus 4. And that is the only function that meets all these expectations. Not only that the second derivative is this, also it goes through the points 0, 4, and 1, 1. Example 5 says the graph of a function f is given in figure 3. Make a rough sketch of an antiderivative f, given that f of 0 is 2. So let's just graph this piece of information because I know that we will forget to do that. So f of 0 is 2, and that will be right here. Okay, this is the point 0, 2. Now, I'm not asked to sketch the derivatives in here and sketch the numerical values of those slopes of the tangent lines. I'm asked to do the inverse of that. This is already the derivative of this function. Remember that f is the same as the derivative of the antiderivative. So if I know how the derivative changes, I can figure out at least one of the functions for which the derivative behaves like that. So important points on this graph are this one, this one, this one, and this one. And those are important points because this is where the derivative of f is 0. This is where the derivative reaches a maximum value. This is where the derivative is 0 again. And this is where the derivative reaches a minimum value. And I just have to find out how it changes in between. For example, in here, the derivative is increasing, but it's negative. In here, the derivative, not the derivative of this graph, but I'm talking about f. If this graph is the derivative, that means that the derivative is increasing and it's positive. In here, capital F prime derivative is positive, but it's decreasing, and so on. So if you are going to start from here, then you want to know how the derivative of f behaves. So in here, if f is the same as capital F prime, in here you know that f prime is negative. So what can you say about f if you know that f prime is negative? The only thing that you can say is that it's decreasing. So from here, instead of going up, you know that it's gonna go down. Okay, that's the first thing that you know. Then ultimately it's gonna become 0 and positive. So wait a minute, when you know that the derivative is negative, then it becomes 0 and then becomes positive, you have a local minimum. So I know that at 1 you don't have to reach 1, but you have to make it a local minimum. I mean, it could be right here. So in here, capital F prime is positive, so that's why the function increases, and then it's gonna reach a maximum and it's still going to be positive, but it's going to be decreasing. So if this in here, you notice how the slope in here is 0, that's the same. So because the second derivative here is 0, the second derivative is positive, and the second derivative here is negative, you can see how at 2 we have a point of inflection, because the curvature changes, it concaves up and then it concaves down. So at 2 we want to make the function concave up, and at 2 is a point of inflection, so it's going to change the concavity. So all the way up to 2 it concaves up, and then at 2 it changes and it starts concaving down. Now at 3 we also have an extrema. You see how it goes from positive to negative. So when the derivative changes from positive to 0 to negative, we have relative maximum. So at 3 I know I have a relative maximum, so I'm gonna make the jump all the way up to 3, where this is the highest point. So definitely from here down is gonna go down. Now notice how the second derivative of capital F is negative, so therefore the concavity is still it still concaves down. And then at 4 we have another second derivative of f to be 0, and you can see how the second derivative is negative and then it's positive. So again, 4 is another point of inflection. So if the concavity was downward between 2 and 4, now the concavity changes and it's upward. Now the last detail that you have to notice about capital F prime, or the antiderivative of f, the derivative of the antiderivative of f, notice how it's approaching 0. So that means that the curve is flattening after that. So I'm just gonna make it flat. It could have become flat here, or I mean, if you're sketching this on your own, your answer could have been like this. It doesn't necessarily mean that it's going to approach 0, it's just flattened, because remember that the derivative of this is what you see here. So it could have flattened at any point. It could have been like this, it could have been like this. The idea is that you're showing that it flattens after, well, in this case I think it's after 5 that it flattens. So then that's it. Any graph that is similar to that will be a good answer. Things that I'm going to look at is if you have met whatever conditions you're given. So the point 02 is important. Then this point is important because it is showing some kind of relative extrema. It could be a minimum, or it could be a maximum. So those are important too, and those have to be seen no matter what your graph looks like. And then the points of inflection are the other thing that we need to look at right here, that you can actually appreciate how it went for concaving up to concaving down, and what are the x values in which that happens. Now example 6, it gives us a physical situation in which we can apply what we have learned, and this is one of my favorite problems, because you can actually have the tools to see algebraically what may be going on a graph. And so let's just recall what we know about position and the derivative of position. When I take the derivative of position with respect to time, then I have velocity. And when I take the second derivative respect to time, second derivative with respect to time, I get acceleration. So we know velocity is the derivative of position, and acceleration is the second derivative of position, or I can say the derivative of velocity. Now, if we know the acceleration, then you know that the antiderivative of acceleration is velocity. And if you know velocity, the antiderivative of velocity is position. So now we're going to work backwards, and you're going to be asked for the function of position versus time, knowing the acceleration. And to go forward, we apply derivatives. So when we go backwards, we apply antiderivatives. And so let's read the problem. It says a particle moves in a straight line and has acceleration given by this formula. Its initial velocity is -6 centimeters per second, and the initial displacement is, which means the position at time 0 is at 9 centimeters. Find the position function. Find the position for any time t. You know when t is 0, the position is 9, but you have to find the position at any given time. So I know what you're thinking. If you know the acceleration is 60 plus 4, then by finding the antiderivative of acceleration, what you will be finding is the velocity. So now I just have to find one of the antiderivatives of acceleration. So velocity is, the antiderivative of 60 will be 6t squared over 2, and antiderivative of 4 will be 4t, and then the cherry on top plus c. Now I can rewrite this as 3t squared plus 4t plus c. Now they give me the condition that when t is 0, v is -6 centimeters per second. So remember that the negative on the velocity means that the particle is going left rather than right. So at the beginning of time, the velocity of the particle is -6 centimeters per second. So I can replace that information here. V of 0 is 3 times 0 squared plus 4 times 0 plus c, and I know that is -6. So this is 0, this is 0, so c is -6. So I know that velocity respect to time is 3t squared plus 4t minus 6. And I know the velocity for any time, and I know every single constant in that formula. I know all the coefficients, so I can find for any given t, I can find the velocity right away. So now to find the position, I know that if I know the position, and I know position, if I know the velocity, I know velocity is the derivative of position. So by finding the antiderivative of velocity, you're gonna get position. So the position function is gonna be, since I'm adding and subtracting these terms, it's just the antiderivative of each. The next exponent is gonna be t cubed over 3 times that 3 that was there, plus the next exponent is t squared over 2 minus 6t plus the cherry on top. Now I'm just going to simplify my coefficients here. I have 2t squared minus 6t plus c, and now I'm going to use the given information. It says the initial displacement is 9 centimeters, so s of 0, which is 0 cubed plus 2 times 0 squared minus 6 times 0 plus c, it was 9 centimeters. So in here this is 0, this is 0, that's 0, so c is 9. So now s of t is t cubed plus 2t squared minus 6t, and I found out that c is 9, so I just put plus 9. And now the position of this particle is well defined at any time t. Now this problem is similar to the one about motion of that particle on a line. However, the only fact that you need to know from physics, and I'm not saying that you took physics, but this is just a feature Earth gravity is something that everyone should know about. The acceleration of anything that falls whenever it's been thrown is 32 feet per second square, or the units in meters is 9.8 meters per second square. So this is the acceleration due to gravity. And whenever you throw a pencil falls off your desk, an apple falls off the tree, you are being thrown from the third floor. Any of those things are falling at an acceleration that is known, and it's the same for every single object. It doesn't matter what the weight is. All of them suffer that acceleration. Since our problem talks about feet, then we're gonna pick this number rather than this one. But this is common knowledge, like 365 days on a year. So we're gonna use that fact and to figure out what is the maximum height and when does the particle hit the ground. So those are the things that we can find if we knew this function h, because the maximum height is going to be given for when the derivative equals to 0, and then as long as I check that, it's going to be a maximum if the derivative changes from positive to negative. So I can find that out. If I know h, I can use h prime. And then when it says when does it hit the ground, hitting the ground means the height is 0, so I want to know what is the t for which h of t is 0. But none of them can be accomplished without knowing what h is. So the idea is to find that function of height that depends on time and then figure out some features of it. So let's see what the problem says. It says a ball is thrown upward with a speed of 48 feet per second. So picture a ball going up at a speed of 48 feet per second. So what would be the velocity? The velocity is 48 feet per second, and you will leave it as positive because it's going up, and up, let's agree that it means going in the right direction. So up is positive, so I can name by velocity. Since it's going up, the height is increasing at this point, so this 48 is a positive 48 rather than a negative. From the edge of a cliff, 432 feet above the ground. So this ball is going up, this is the cliff, 432 feet, and this is the bottom of the cliff. Okay, it says find the height above the ground t seconds later. So they are asking me for h of t. What is this function h of t? And then we're going to be able to answer the other questions that stem off of it. Okay, so I know that the acceleration for any object that has been thrown is 32 feet. So I'm going to use that. Fact. So a of t is 32. However, the acceleration is not making this ball go faster, but it's actually going slower every time until the velocity is 0, and then it starts falling. So this acceleration is working against this ball, and it's keeping it from going up and into outer space, and it actually brings it back down to Earth. So the acceleration here is negative 32 rather than positive 32. So, and this is constant. So I know that v of t is going to be negative 32t plus the cherry on top. Now, since I know that at the beginning the ball was thrown with this much velocity, I know v of 0 is 48. So when I replace it here, I equal it to 48. I discovered that c is actually 48. So I know the velocity that depends on time at any given time is negative 32t plus 48. All right, now I know that the height, when I take the derivative, is velocity. So if I know the velocity, I can find the height by applying again antiderivatives. And that's what I did. From acceleration to velocity, I did antiderivatives. So the exponent now is going to be, instead of 1, 2, negative 32 t squared over 2. Now the exponent is 0, so now it will be 1 plus the cherry on top. And simplifying, this is going to be negative 16t squared plus 48t plus c. Now, from the given information, I know that at the beginning, the height of this ball is 432 feet. So I know that at time 0, which is negative 16 times 0 squared plus 48 times 0 plus c, the height was 432 feet. So now this disappears, so c is 432. So the height that depends on time is given by negative 16t squared plus 48t plus 432. And this will give me the height in feet. Okay, so I actually found the first part of the question that said find the height above the ground t seconds later. So t seconds later is this much. Now it says, when does it reach the maximum height? So you know from the properties of quadratic functions, this is a quadratic function where a is less than 0. That means the parabola opens down. So it's going to have a maximum. So I don't have to worry about finding the sign change of the derivative if it changes from positive to negative to have a local maximum. I know that once I take the derivative of this and I equal it to 0, that value is going to be the value that that is going to be the absolute maximum. I don't have to check all the other things. If this wasn't a parabola, if this was some other function that I don't know how it behaves, especially with rational functions, then you have to verify that the derivative in here, that h prime, changes from positive to negative for you to say, okay, that's going to be a maximum on the height. Okay, so I know that the derivative of height was here, velocity, so I'm just finding when the velocity is 0. For what t the velocity is 0, because that's where it actually reaches the maximum height. Think about it, a ball leaving, you know, the edge of the cliff at 48 feet per second going up. When does it start to go back down? Well, when the velocity is 0. It stops, the height stops increasing and then starts decreasing. So when I solve for t is actually negative 48 over negative 32, and when I simplify that, is 1.5. So that means after, and this is what I have to write, after 1.5 seconds, it reaches the maximum height. Oops, sorry, you can't see that. It reaches the maximum height. Now, the problem doesn't say how much is that maximum height, but just to give the reader the impression that you are understanding what it is that you're doing, it is always helpful to find the actual maximum height. You know that it's been reached at 1.5 seconds, but you haven't said how much is that actual maximum height. So the only thing that you have to do is find what is h of 1.5. You want to know what is h of that time in which it reaches the maximum height. So h of 1.5, you will just replace the negative 16 times 1.5 squared plus 48 times 1.5 plus 432. And according to my calculations, chin chin chin, you put it on the calculator. After calculating how much the maximum height is by replacing 1.5 into h of t function, I get that this is 468 feet. So after 1.5 seconds, it reaches 468 feet, and that is the maximum height. You don't have to if it doesn't say, but it will be nice to have. And also, if they ask you, that's how you do it. And then the other question says, when does it hit the ground? So you just have to make h of t equals 0 and solve for that t. When you do that, you have negative 16t squared plus 48t plus 432 equals 0. Then you notice how 16 goes into everything, so I can just divide the entire equation by negative 16, and that includes also the right side of the equal sign. So I have t squared minus 3t minus 27 equals 0. Now the numbers are easier to see if it can factor out or not, because that will be the easiest thing to do. However, this doesn't factor. I can't find two numbers, so that when I multiply them gives you negative 27, and when you add them gives you negative 3. So the only way to go will be to use quadratic formula. So with quadratic formula, you have negative of b, which would be positive 3 plus minus b squared, which is 9, minus 4 times 1 times negative 27 over double of a, which is 1, so it will be 2. So it would be 3 plus minus over 2 of 3 rad 13. Now this is something that you just have to use the calculator, because you don't know when this is going to be positive or negative. Since you are using time, then you want your answer to be positive, so therefore you will discard the negative answer. So figure out what is 3 minus 3 rad 13. I think it's a negative number, so you will go with the positive solution. So approximately the exact time will be 3 plus 3 rad 13 over 2. But since they are asking us for time, you don't know how many seconds is this. So approximately the time will be 3 decimals is fine. Now when you're dividing by 2, please make sure that you do put parentheses. You want to do 3 plus 3 rad 13, and then close that, and then divide by 2. Because if you only put it at the end, you will only be dividing by 2 the second summand. So that's about 6.908 seconds. And that's all.